class, which at least the first part of today's class, which we will keep, we don't have that much to do. We're going to complete our discussion of the computation of S matrices. Okay, so at the end of the last class, we discussed the BRST cohomology. So we discussed the BRST current, and we talked about how the states that we're going to allow to scatter will lie within BRST cohomology. So we know what we want to scatter. What we have to get straight is the analog of this integrated vertex operator and on an unintegrated vertex operators. First, let me remind you, in the case of the bosonic string, we had a bunch of C bar times O's, some number of insertions of these, and times some number of insertions of D2Z O's. The O's were always matter 1,1 primaries, okay, and the O's were always matter 1,1 primaries. This guy was within BRST cohomology, and this guy also in some sense. Okay, so we had the insertion of these, and how many such insertions we had, depended on which genus we were on. Okay, on the sphere there were 3 of these, and these were the rest. This is on the sphere. On the torus, we would require 1 of these, and these would be the rest. Okay, and on any this is torus, and on any other higher genus surface, on any other higher genus surface, you have none of these, and these are the rest. And this came, for instance, from it came from our derivation of the path integral, but you can also get it in a quick and dirty way by just looking at the number of C0 modes. Okay, the number of C insertions had to just match the number of C0 modes in the path integral, and we computed the number of C0 modes. If you remember, the number of C0 modes was 3 on the sphere, 1 on the torus, and 0 everywhere else. And then there were additional issues having to do with integral over moduli, the B moduli. And every integral over a modulus then was accompanied by an insertion involving B, this inner product of B with del G by del T. And one way of understanding that had to be was that on a genus G Riemann surface, there are exactly as many B0 modes as there are moduli. Okay, so the B0 modes would otherwise kill the path integral, but if you have as many insertions as B of B as there are B0 modes, you get a non-zero answer to the path integral, and it was a beautiful story that worked out nicely. Okay, now fine. So the first thing that we have to understand here is what is the analog of this and this for superconformal fixing. Okay, and I'm just going to tell you the answer, and we'll check it makes sense. We're not going to derive it from the path integral like we did last time. But I'm just going to tell you the answer, and we'll check that it makes sense. And the answer, we'll try to guess the answer by analogy. Okay. So firstly, what was this object? This was the object that was the state, the operator dual to the matter oscillating state by the state operator map. Okay. So why did we have that e to the c, that c is c bar? Because the ghost vacuum was dual to c bar. So in the superconformal sector, once again, the idea is going to be that there's going to be what we're going to think of as an unsuper integrated. We'll see exactly what that means in a moment, but an unintegrated vertex operator. And that, let's say we're dealing with a vertex operator that is unintegrated both in space-time as well as in superspace. So that would be c bar, e to the power, what was it, plus or minus phi? The thing dual to the minus? Yeah. Okay. So e to the power minus phi, e to the power minus tilde, whatever, bar, times some matter operator. Okay, and we checked, for instance, in the sense of level, that such things lay inside BRST cohomology when I'm working now on the NS sector. Okay, such things lay inside BRST cohomology when this was a half comma half matter operator, right? This has dimension -1, this had dimension half, so this has to have dimension half. Okay, so these are, we will choose the O's to make these nice BRST operators that lie inside BRST cohomology. Okay, this whole object here will have to be BRST closed. This is the analog of the unintegrated vertex operator. Now, what is the analog of the integrated vertex operator? Well, you see, what we're going to do is this. You remember in our discussion of superspace. Our discussion of superspace, we had, for instance, we had, let's say when we were dealing with the X field, we had X plus theta psi plus theta bar psi bar plus theta bar F. Okay? Now, or in general, when you had a superconformal primary, you had, let's say, a holomorphic primary, you had O plus theta, let's call it psi, fermionic partner of this O. Okay, now the supersymmetry generator, you'll remember, was del by del theta minus z theta. Del by del, that's it. Thank you. Okay.
Psi is not same as the psi.
No, not same. This is psi O, the superconformal partner of this. Okay. So when acting on X or on one of these O's, if we want to act with supersymmetry on one of these guys, one of these primaries, we have to act with this guy. Okay, but you see, suppose I wanted to act with this guy and then finally evaluate it at theta equals 0. So I want to act with the supersymmetry operator and I want to evaluate it at theta equals 0. Okay, then it's only the derivative that will operate. Okay, which is giving us the familiar statement that the action of supersymmetry on O will be what you get by taking the derivative of this, and therefore will be psi. Or the action of supersymmetry on X. Okay. Why did I want to evaluate it at theta equals 0? Because I wanted the action of supersymmetry on O. Right? You're supposed to pull out the theta equals 0 component. You act with the supercharge, and the resultant expression will be a function of theta. Then you put out the theta to the power 0 if you want the action on O. You pull out the theta to the 1 if you want the action on psi. So we're not interested in the action on psi, we're interested in the action on O. So that is simply by acting with the supersymmetry part. The only part of the supersymmetry that counts is this del by del theta. Okay? So for the particular question that we are interested in, namely the action of supersymmetry, the zero, action of supersymmetry on this, just wherever's at the bottom, you can replace supersymmetry just by del theta. Okay, but del by del theta same as integral with respect to theta. Okay, so suppose we were interested in, we thought that the analog of this in our minds is d2 theta of O. That is the same thing as Q and Q bar acting on O. Because, okay, now you might remember that we had these, this TF, the superpartner of the stress tensor, and that was expanded as sum over n gn by z to the power n plus 3 by 2. Sum over n, right, exactly. And our n's were either integer moded, or half integer moded, depending on whether we are in the Ramond or the NS sector. In the NS sector, it's half integer moded. Okay? And the thing that was the supersymmetry operator, was the part that gave the pole in Z of this guy, and so was G minus half. Okay, this is the analog of the statement that energy was L0, or momentum, actually more clearly, momentum was L minus 1. Right, the momentum operator was L minus 1, the supersymmetry operator is G minus half. The minus half is keeping track of the fact that the supercharge carries energy dimension minus, energy dimension half, or length dimension minus half. Just like momentum carries energy dimension 1, that's why it was L minus 1. Okay? So another way of saying this, this same thing here, is to say that this is G minus half, G tilde minus half, acting on O. I've just written the supersymmetry operator in terms of TF, in terms of the moments of TF. It's a particular moment of TF. Okay? So this, using this analogy, we are going to propose that what replaces the integrated vertex operators is G minus half, G tilde minus half, acting on O. Okay, where G is the moment of this, the half minus half moment of the TF current. Okay? So, with this picture in our heads, we're going to think of the scattering amplitude like this. Okay, there are going to be some number of vertex operators that are fixed or unfixed in the bosonic sense. Those, how many are fixed and how many are unfixed, the rules have not changed. It's 3 fixed on the sphere, 1 fixed on the torus, none fixed. Okay? However, whether a vertex operator is fixed or unfixed in the super sense has nothing really to do with whether it's integrated over or not. It's just a question of whether you're inserting O or G minus half, G tilde minus half or no. Okay? So the choice of whether it's fixed or unfixed in a super sense is unrelated to the choice of whether it's fixed or unfixed in the bosonic sense. We will show in a moment that you can transfer, you move around from which one is fixed to which one is unfixed. So the idea is going to be that the vertex operator is going to be, so I'm going to say it on the sphere for a moment. Okay? Just to be concrete. Okay? There are going to be 3 fixed vertex operators, C, C tilde, O, C, C tilde, O, C, C tilde, O, C, C tilde something. And then there are going to be lots of unfixed vertex operators, again of something, where all of these somethings will be either the superconformal primary of either the superconformal primary of dimension half.
Is it to a minus 5 also?
What?
Is it to a minus 5?
Yes. So either the superconformal primary with e to the power, yes. So either we will have e to the power minus 5, e to the power minus 5 bar times O. That's one possibility. Or we will have, or g minus half, g minus half tilde, or no. You see, here you don't put the e to the power minus pi, e to the power minus pi bar. Just like here, you didn't have the CC bar. Okay? So you have either this or this, and which one you choose needn't be connected with whether the corresponding operator is integrated or not on the well sheet.
So this integral is equivalently integrated over theta and z, but theta integration we can do.
We've done that exactly
We can do to get this g up.
to get this business.
But the integral is
It's still there, the integral over z is still there. Okay? Now the next question we have to figure out is how many of our vertex operators, next question we have to figure out is how many of our vertex operators are integrated over over superspace, how many of them have this form, and how many of them do not. Okay? So now the first thing we want to do the key difference here in order to figure this out is just this of the following observation, that this part is purely in the matter sector, whereas this part has superconformal ghost contributions as well. Okay? Now, this allows us to figure out immediately how many have to be integrated and how many not. Okay, how do we figure this out? Well, remember that 3 or 4 classes ago we derived the stress tensor in the phi sector. I'll just pull it out and remind you what it was. The stress tensor for the phi was TB phi was equal to minus half del phi, that's the usual, but then there was lambda prime is 3 by 2, so minus 3, so 1 minus 3 minus 2 minus 1 minus del squared phi. Okay, so the stress tensor for this system was the stress tensor for a scalar field with a background charge, this linear dilaton kind of scalar field. Okay, now in the last semester we went through a little calculation, but I will briefly remind you of it. Okay, in the last semester we went through a little calculation which you remember that there is this translation current del phi, J is equal to del phi. And this translation current, it's a holomorphic current, so in flat space it's conserved. Okay? But we showed that if you looked at del mu J mu on a curved manifold, because of this extra term in the stress tensor, had we just taken del mu J mu for a free boson with the stress tensor, we just get 0, and that 0 was genuine 0. Okay, but we because of this we got some number times r. I'll very briefly remind you of the logic for this. But you remember we did this for the BC system, for instance. JBC, del mu J mu BC was equal to some number times r. And this is the same calculation because the BC system can be bosonized into a boson with such a stress tensor, and in fact the current, the BC current, maps to this under bosonization. It's the same calculation, the calculation we did in the last semester. In 2 minutes I'll briefly remind you how that went. Okay, but now what's important is to understand logic first before doing a calculation. Okay, So now, since this is the case, okay, since this is the case, if we take this object and integrate it over the whole, so now suppose we're on some genus G Riemann surface. Okay, we're on some genus G Riemann surface, and we've got insertions of operators, let's say O1, O2, O3, O4, which carry charge Q1, Q2, Q3, Q4 under this translation charge related to this current. If del dot J had been 0, by integrating this equation, we would find the equation that Q1 plus Q2 plus Q3 plus Q4 had to be equal to 0. Okay? Now with this modified equation, that 0 is replaced by whatever's on the right hand side, integrated. But the thing integrated on the right hand side is something related to the genus. Right? It is whatever, what was it? 3g minus 2? Proportional to something like this, right? 3 minus g minus 1? Yeah, sorry, 0 in the torus. 3 into g minus 1, exactly. Because the torus has 0 curvature. It's proportional to this, and then you get some number. Okay? And the number, when you work it out carefully, works out so that this thing turns out to be 2 on genus 0. Okay? So the net formula is the total ghost charge, the total charge, okay, measured such that e to the power minus phi has charge 1. So it's a minus 2. So total e to the power minus phi charge. It's clear that this guy carries charge minus 1 under del phi. Right, because you translate, you get charge 1, minus 1. So the total number of powers of e to the power minus phi, okay, has to be equal to 3 into g minus 1 times the number that will make it 2. So suppose I put g equals 0, you get minus 3, so I'll get minus 2. Okay, so let me say this more. The total suppose you have e to the power, e to the power a phi 1, a phi, e to the power b phi, e to the power c phi, and I define the total in charge as a plus b plus c. This has to be equal to plus 2 into g minus 1. Okay, so that the total charge on a genus 0 surface is minus 2, so 2 insertions of e to the power minus phi. That's the data point I'm reconstructing the answer from. Okay, it's just a question of what this number works out to, and this number happens to work out so that that's true. We'll go through in 2 minutes roughly the logic for how to determine that number. Okay, so this tells you then how many e to the power minus phi insertions you need to have. Okay, it tells you that on the sphere the total number of unintegrated vertex operators has to be equal to 2, because it's the unintegrated vertex operators that carry e to the power minus phi charge, and the integrated vertex operators that carry no e to the power minus phi charge. Is this clear? Okay. In a similar manner, it would tell you that on the torus, the total number of unintegrated vertex operators has to be 0. Okay? And it would now start demanding negative numbers of unintegrated vertex operators on higher genus surfaces. So now this sounds good so far, but has led us to what looks like a puzzle. Looks like what we've said could work on the sphere, could work on the torus, but what do we do when we go to higher genus operators? Okay, and in order to understand that, we're going to, okay, so let me postpone the discussion of this for to the end of the class. Let me get the whole logic right, because we'll just get waylaid into some algebra and you'll forget what we're trying to do. Okay, so let's get the logical structure right, and then we'll come back to this little calculation. Okay.
If G is 0, then there should be 2 e to the power minus 2, 5. 2 e to the power minus 5.
Exactly, 2 e to the power minus 5.
Okay, so this, when it has 2 e to the power minus 5.
No, this is each
copies of.
for holomorphic and anti-holomorphic. Just forget the anti-holomorphic.
Then this kind of
Two operators like this. Okay. Now, okay. Now, to understand how to deal with these, higher genus, higher genus amplitudes, what we're going to do is to understand what is called these picture changing operators. Okay, this is absolutely the last complication we're going to deal with before we now start studying physics. Okay, there are a few more complicated technical things, but we'll just postpone that to when we need it. Okay, I know it sounds like a never-ending cycle, right? I mean, just to understand how to calculate scattering amplitudes, you have to do more and more technicalities. Okay, and it is like that. I mean, to an extent. I mean, you guys should be happier studying the NSR formulation. If you try to study the Berkowitz formulation of string theory, oof, the complexities. I mean, Berkowitz claims to understand it, but okay. But okay, okay. You know, so it is a very complicated subject. But, you know, the complications are finite. Once you've got them, as you see, when you can actually use it to do calculations. Once you've got the mind map of it, they're not complicated. So you're always dealing with free theories. Okay. So the last thing that we need to do is as follows. I'm going to give you another way of thinking of these vertex operators, these integrated and unintegrated vertex operators. And this other way goes by the name of picture changing operators. We're going to go through that. But before we start going through it, let me just introduce the terminology. A vertex operator that has a factor of e to the power minus 5 is said to be in the -1 picture. So in this a vertex factor that has no factor of has a factor of e to the power 0 times 5. I mean no phi dependence is said to be in the 0 picture. So in this terminology, the original vertex operator, the one that came from the state operator map, was in the -1 picture, and the integrated vertex operator is in the 0 picture. What we are going to try to do is to show that there is a way of defining vertex operators in any picture from -infinity to infinity. At least from -1 down to +infinity. I'm not sure. -1 to +infinity. Okay? And this will allow us to solve the puzzle with the higher genus surfaces, because what we needed to do is to have insertions not of negative powers of phi, but of positive powers of phi to satisfy that equation. So with these two kinds of vertex operators, we can't do it. But if we can get analogous operators so that it won't matter when calculating scattering amplitude, but with positive powers of phi, then we'd be in business. Okay? So that's the game. So that's the game, and let's play that game, and we'll come back to this issue later. Okay. So in order to play that game, I'm going to remind you of the bosonization of the superconformal hosts. Recall we had the beta gamma system. The beta gamma system was a system with beta is equal to, has dimension of beta was equal to 3/2, and dimension of gamma was equal to half. Its action was just given by beta del gamma. Okay, simple. The OP was simple. Beta with gamma was 1/z, gamma with beta was -1/z. All that you remember. What was interesting was that we were able to bosonize this. Okay, and our bosonization went as follows. Beta was equal to e to the power minus phi. This is the same phi that appears here, times del zeta, and gamma is equal to e to the power phi times zeta, times eta. And you will remember, or I will remind you, that the weights, one of them had weight 0, one of them had weight 1, and I'll just remember which is which. Eta is 1 and zeta is 0. The weight of eta was 1 and the weight of zeta was equal to 0. Okay, and we already have the formula on the board for the stress tensor of e to the power minus phi, so this gives you everything. Just as a quick check, the weight of this is minus half. No, sorry, is plus half, right? Plus half, plus 1, so that's 3 by 2. And the weight of gamma is, let us remind ourselves of the weight formula also. The weight was the weight of e to the power a phi was equal to minus a squared by 2 minus a. So if we said a equals minus 1, this is minus 1 plus, it's 1 minus half, so half as we said. But if we said a is equal to plus 1, that is relevant for this, we get minus 1 minus half, so minus 3 half, minus 3 half plus 1, so that gave us minus 3 half plus 1, so that gave us minus half. That's the right answer for this. Right? It was BC was 2 and minus 1. The beta gamma was 3 halves and minus half, shifted by half each of them. Okay. Now, because this was the bosonization, okay, okay, if we wanted to do an integral over before proceeding, let me remind you of the following thing. Let's count the number of, let's work on this, let's work to start with on the sphere, okay, and count the number of zero modes of zeta and of eta. Okay, let's go ahead and do that. Okay, so the number of zero modes of zeta on the sphere was, or on any genus surface, was always equal to 1. Why? Because zeta has weight 0, so it behaves like a simple function. Any simple function has one zero mode on any surface, namely the constant. Okay, but in general, the number of zero modes of something with a weight is different. Do you remember how we how we checked what the number of zero modes of B and C were on the sphere? Let me quickly go through that calculation for you in the context of zeta and eta. Suppose I've got something of weight m. Okay, what does it mean? It means that it transforms under conformal transformations like a derivative. So, like a derivative to the power m. So let's remind ourselves that del by del z. So conformal. So let me start with the logic. The logic is this: a zero mode is a zero mode that is well behaved all over the sphere. We're going to take the sphere and look at it as the sum of two different patches, always working in stereographic coordinates. So on one patch, our coordinate is z. That's the patch that includes everything but infinity. On the other patch, our coordinate is 1 by z. That's the patch that includes everything other than the origin. These two patches completely give us the sphere. Okay, so in the Z patch, clearly the mode has to be, whatever your mode is, it has to be analytic, it has to have a Taylor series expansion. But it also has to have a Taylor series expansion, the 1 by Z patch, but after doing the appropriate conformal transformation. Right? So now suppose we take del by del Z. Now, and Z prime is equal to 1 by Z.
So we got minus 1, 0 and 1.
We got minus 1, 0 and 1, but there we used the fact that C had weight minus 1.
I'm saying it for L0, L1.
What?
L0, L1 and L minus 1.
L0, L1 and L minus 1. No, this is going to be a question which will depend on the weight of the field. Let's just go through the calculation. Okay, so Z prime is 1 by Z. Okay, so del by del Z prime is equal to del Z by del Z prime times del by del Z. That's the chain rule. But Z is so Z was 1 by Z prime. So del of, so that's minus 1 by Z prime squared times del by del Z, which was equal to, if we want, Z squared times del by del Z. Okay? So if we have a field of weight 1, okay, then if we had a field of weight m, then B in the Z prime coordinate, that's like del by del Z prime, is equal to Z squared to the power m, because you get one such factor for each weight, times B in the Z coordinate. Is this clear? This is how conformal transformation will cause the field to transform. Okay? So now we want, if we've got a field of weight m, and we want it to be, okay, so we want to see what possible zero modes there can be. The zero modes in Z are going to be am Z to the power m okay, anything that's analytic was a zero mode in the action, right? Because it was B del C. Okay, so we want these analytic fields, these analytic vector fields that that are zero modes of the action, but they have to be well behaved. So this is with m greater than or equal to 0. Okay, now we have to transform this to Z prime coordinates. So we get am by Z prime to the power m, but multiplied by 1 by Z prime squared to the power m. Is this clear? Now, if m is positive, it's some positive integer, then, sorry, I used m for two different things, let's call this k. This is sum over k. You understand, right? This is a formal sum. If k is always positive, if m is positive, this thing for every k, 0 to infinity, will be ill behaved at Z prime equals 0. So there will be no zero modes. Okay? If k is 0, sorry, if m is 0, then there will be exactly one zero mode, namely the one with k equals 0. Okay? And if m was negative, then there would be more zero modes. For instance, if m was minus 1, this was the case for the C ghost, then because of this factor of then we would get Z prime square times whatever we had here, and so k equals 0, 1 and 2 would be well behaved modes. Those are the three zero modes of the C ghost. Okay, but now in the current context, in the current context, we've got zeta and eta. Eta is weight 1, so we're fine. There are no zero modes there. Okay, but this quantity zeta here, this guy has exactly one zero mode on the sphere, and in fact on every dimension, on every Riemann surface. Is this clear? Okay, this guy will also develop zero modes on higher dimensional Riemann surface. We'll have to deal with that, and we will in a bit. Okay, but for now, forget about it. I want you to focus on the zeta. We see that zeta has exactly one zero mode on every dimensional Riemann surface. Now we see that our formula for string scattering amplitudes has a problem. And the problem is that what we did was put lots of insertions, but none of them involved zeta. Because we put insertions involving phi, that was the extent to which the superconformal hosts participated. But phi is different from zeta. Okay, so if we do the bosonization, we convert this into a path integral over phi, we can try to saturate enough phi insertions to make the phi integral converge, be well defined, non-zero, so on. But the zeta integral will still kill us. It will just give us 0. Because on the sphere, and in fact on every dimensional Riemann surface, because it's weight 0, there is a zero mode. Is this clear? Okay, so our formula for the string scattering amplitude cannot quite be right. Okay, so what do we have to do instead? Actually, what we do to fix it up is very simple. We just put an insertion. So I told you that there were many insertions. There were insertions of e to the power minus phi, e to the phi o, some c's, and there were some g minus half, g tilde minus half o's. Okay? Now, in addition, just choose any point on your Riemann surface, let's call it z0, and insert a zeta of z0 into that path. You might ask, where does this come from? Actually, if you carefully analyze how you go from a beta gamma path integral to a zeta eta phi path integral, that factor is needed. Okay? For now, take this from me, and when we need this more carefully, we will come back to understanding where that came from. But at the moment, just as a prescription, we just add this insertion of zeta of z0 for any z0 there. So we've got these vertex operators, they're all over the place, and then we add this factor of zeta of z0 by hand.
What is z0?
Good question. What is z0? The answer is it doesn't matter. Because you see, the path integral over zeta and eta is non-zero only because of the z0 insertion. So the z0 insertion saturates the zero mode. Do you know what I'm talking about? We discussed this at length when discussing BC. The path integral over all zeta eta can be thought of as follows. Decompose the zeta eta fields into an eigenbasis of your derivative operator. Okay? And the path integral is the same as the integral over the coefficients of this decomposition. Are you understanding what I'm saying? Is this familiar? Let me remind you. We work this out in the context of the BC system, so I'll say it in that context, though it doesn't matter. You remember that we could think of this operator, the BC system was BPC, where P is this operator which is basically del by del z, right? Anyway, we could write this in covariant form. Okay. Now, this is like a rectangular operator because it was an operator that took a one form a vector to a 2 tensor. Okay? But this could also have been written as P dagger B times C, more or less by definition. Okay? And then we looked at the operator P dagger, which was now a square operator. So this operator was a square operator and we diagonalized that. Okay? You remember that P dagger had the same spectrum as P dagger P, apart from the zero modes. Okay? That the zero modes of P dagger were zero modes of this operator, the zero modes of P were the zero modes of this operator. Other than that, they had exactly the same spectrum. Okay? So when doing the path integral over C, okay, so we took the so this was some operator which, let's look at the common eigenvalues. So there are some operator eigenvalues lambda m. So let's say P dagger lambda m is equal to zeta m am lambda m, where lambda m is some wave function. Okay, the case where am is 0 is special. Put that aside for the moment. All the non-zero ams are something, are a spectrum, and you remember that the spectrum of P dagger P, the non-zero part of the spectrum of P dagger P, was the same as spectrum of non-zero part of the spectrum of P dagger P. Went through all this in great detail, right? Okay. Now suppose we're interested in doing the path integral over C. We look at the operator P dagger P. So then there is these. So what we do is to take the C field and write it as a sum over Cm times lambda m, but these lambda m's were both the non-zero guys, and then plus the special zero modes, C0 times lambda 0, C0I times lambda 0I. There may have been many zero modes. Any C function could be decomposed like that. Now the path integral over the C functions was just sampling all possible functions. One way to sample all possible functions is to take all possible coefficients. So path integral over all C's was same as product over M dCm integral over Cm's. Also, of course, we have to include these Cm's include these C0i's. Now from this point of view, why does a zero mode die? It's because C0i does not enter the integrand, precisely because it's a zero mode. It integrates to 0 because it's a fermionic path.
But you have to insert one C.
We have to insert one C, but before the insertion of the C, it integrates to 0. That's why we had to insert a C. But now notice that when we insert a C, that C is expanded like this. It's Cm lambda m. But the only part of that expansion that clicks is the C0. So even though you're inserting a C, it's only the zero mode. So the answer is proportional to the wave function of the zero modes. Okay? That is what, after you've done that insertion, the insertion will give you a factor which is equal to, its position dependence is the position dependence of the zero modes. And then the remaining integral you have to do is over the non-zero modes. Okay? That was the whole role of these insertions. You could replace them by the zero modes. Now, that's very good, but in this particular case, zeta is very special because it has dimension 0. So the zero mode, there's one zero mode of zeta. And what is the zero mode? It's a constant. So that insertion there in the integral will give you an answer that is constant and therefore independent of z0. It's constant. So it doesn't matter. And that's why it's a sensible prescription. Is this clear? Okay. So the final answer is that we're going to take this and add this zeta of z0. Now, this may worry you. Okay? This may worry you for the following reason. One of the key features of the string scattering amplitude is that if you try to scatter something that is pure BRST exact, you try to scatter something that in the form of a vertex operator is JB at a contour of JB circling some other insertion. So that in operator language is QB commutator, that operator. One of the key features of this, of string scattering amplitudes, one of the features that we will soon in detail check for our amplitude. Once we've got the final prescription clear, we'll check that it obeys all properties. Okay? But one of the key features, of course, is that it's BRST invariant. Namely, that if you add one of these insertions, you will get 0. Now, what is the logic? What is the contour logic? What is the worldsheet logic? Why was it 0? Why was it 0 for the bosonic string? The reason it was 0, there were some caveats you had to go through. But basically the reason it was 0 is that you could take this contour and deform it. Now in the process of deforming, you'd encounter other vertex operators. You have to circle those other vertex operators and then you'd close off your circle to the other end of the sphere and get 0. Now the action of the other vertex operator is simply the action of the BRST charge on the other vertex operators. Because it's JB surrounding some vertex operator, which by definition is BRST charge acting on that vertex operator. Which was 0 because we were only scattering BRST invariant things. Was this clear? Was it too fast? Schumann, was it clear? I'll say it again. Suppose we've got this and some other operators on a sphere. These operators are all BRST invariant. I want to show that this gives you 0. Okay? Now, let's assume everything was BRST invariant. There's some caveats, but right now. So what do? I take this contour and I try to deform it. You know, imagine that this is a sphere. I try to take this contour which is here and take it round to the other end of the sphere. Then I get 0 if I can do that. But because these other operators are here, I will end up circling these guys and then get 0. But this guy circling around these other operators is by itself 0 because it is the action of the BRST operator on these operators, which was 0 because they were BRST invariant. Therefore, if we've got only BRST invariant insertions and the operator that then we try to insert a null state, we get 0. This is the worldsheet way of saying that. Is this clear? Now in this context, we have insertions of all kinds of other operators. But we also have this zeta of z0. So all of these are 0, but in addition to everything else, when we try to take this BRST charge thing and pull it around to the other end of the sphere, we will get a factor of JB acting on zeta. Okay, we'll get a factor of JB acting on zeta. Okay, the BRST charge acting on zeta. Okay, so now we might worry whether these were 0. However, try this as an exercise. Check that Q BRST on zeta, whatever you get from Q BRST and zeta, has no zeta 0 mode. We get something, whatever appears here does not involve the zeta 0 mode. So now we are saved because you say this operator was non-zero. Okay, just take the explicit form of QBRST or take the explicit pole in JBRST with zeta, compute the pole. Okay, and check that in that pole, it's basically because the pole comes when you have a beta hitting the zeta, eta hitting the zeta. Okay, that eats up the zeta itself. So what's left behind has no zeta with it. Anyway, just check. Just check that this thing has no zeta 0 mode. So even though you get some non-zero operator, its integral under zeta kills you because the integral of the eta 0 mode. Is this clear? So this insertion had two possible problems. A, that it could depend on where you made the insertion, but because it was a 0 mode, it didn't. B, that it would ruin the decoupling of BRST trivial states, but for the reason that we talked about, it didn't. Okay? However, we're now in the process of making this argument, this interesting operator comes up. The interesting operator is what you get by circling zeta with a BRST current. Okay? This operator is given a name, it's called X. So zeta with JBRST around it is equal to X. And that's given a name and it's called the picture changing operator. Okay. Now I want to argue, meaning that this, it is still true, even though we made this insertion here, it is still true that the insertion of any BRST trivial state under the path integral gives you 0. You see, why did it happen to be 0 before? It happened to be 0 because you could deform the contour, each contour surrounding an operator was vanished, and then you could deform it to the other end of the sphere. Now you can still do that, but you're left over with something. You're left over with something non-zero. So it's not 0 at integrand level, the way it was before, but it's still 0 at integral level because it doesn't involve zeta 0 mode. So you get 0. Okay? So two possible immediate objections, neither of which are hold water. Is this clear? Now, I'm going to do two formal manipulations, and then we will see what physics we've learned, what we've learned from this. The first formal manipulation goes as follows. Suppose I've got some insertions. I've got the zeta insertion, zeta of z0. And for some reason or the other, we'll see why, but for some reason or the other, I put an insertion of x at z1. Suppose I did that. X is this zeta with BRST charge going around it, BRST current going around it. Okay? And let us suppose that all my other insertions are BRST exact. Let's suppose that's the case. Then I want to know whether the result of this path integral is 0 or not. Okay? I'd already argued for you. You might think, of course it is, because we had an argument that anything involving a null state gives me 0. But we have to be careful because we implicitly assume that the null state that we had was a null state of something which itself did not involve zeta. Otherwise, this argument that the zeta integral will kill you is not true. It was a null state of some matter field. That was what we had in mind in the early argument. Now we're doing something very similar, but this insertion, it's a null state of zeta. So now let's replay the same argument again in our head. We take this contour and we deform it around. The deformations around each of these points give 0 because they're BRST invariant. This guy is non-zero. And then I can go and take it around the sphere. Now, this is not 0. It's not 0 because as we argued that this quantity, x on zeta, had no zeta in it, no zeta 0 mode in it. That was the argument we used to show that there we were saying. This guy did. What we've ended up doing is transferring this contour from here to here. So now this guy will have no zeta 0 mode, but this guy will. Okay? So, you should think of QB is roughly being in its action on zeta like being like a 1 by del by del zeta. So QB is reducing the power of zeta by 1.
You are saying this x replaced from Z1 to Z0.
Exactly. Through this manipulation.
And it will come to zeta again.
Exactly. But we already know that this path integral here, the answer to this path integral, this by itself is some BRST invariant operator. Because it's BRST acting on something. It doesn't matter whether it's zeta or not. So the old argument told us that the answer here to this path integral did not depend on the position of the z zeta naught. Because this is in particular some other BRST invariant operator. But now we've moved this guy to here. So what we've done is interchange which one was the x and which one was the pure zeta insertion. Since the answer did not depend on the position of the pure zeta insertion, and since you can interchange them, it follows that it also does not depend on the position of the x insertion. Okay? So now we're beginning to come to business. We have this lovely operator, this picture changing operator, such that we can put somewhere on the world sheet. No claim that putting it gives you 0 or anything nice. But what we have learned is that the answer, whatever it is independent of where we put this BRST invariant operator. This picture changing operator. Okay? Now, these insertions here were supposed to be BRST invariant. These insertions here were supposed to be BRST invariant. So they were the original -1 picture operators. The operators that came from the state operator map. You might remember that even in the case of the bosonic string, it's C times primary operator that was genuinely BRST invariant. BRST invariant of vertex operators worked only after integration. The BRST transformation of them was not 0, but was a total derivative. You might remember how that worked out. Or you can remind yourself of that. Okay? Here, but the primary operator, the one right at the bottom of the Verma module, is by itself just genuinely as an operator BRST invariant. So we've got to make all these arguments work, we wanted all these insertions here to be the -1 picture operators. And then if you want these additional picture changing operators, you could put 1, you could put 2. Answer won't depend on where you put them. It will depend on that you have them. Won't depend on where they are. Okay? And you get something. Now I want to understand what this something is. In order to do that, what I'll do is to take this operator, since it doesn't depend where you put it, I'll take it very near one of the operator insertions. So suppose this operator was O at 0. Okay? And then what I do is I take this x operator at z near it. Is this clear? Okay? Now I want to compute what I get when I do this. Okay. So let's go ahead and do that. Now this O here is built totally out of matter fields. Okay, so let us pick yeah. So let's as we've seen before, this O here, this O was e to the power minus 5. Let's just work on the holomorphic side. This is e to the power minus 5 times O matter. Okay? And what we want to do is to take this BRST operator and bring it near here. Take this x operator and bring it near that. Okay. Now, e to the power phi df. Let's look up the formula. Yeah, we need the formula. Sorry, just one second. We need the formula for what happens when JB hits the zeta. Sorry, just one sec. Oh, where is that? Just one sec, sorry. All right, let's just compute it. I'll just get the formula for the BRST current. BRST current. Here. Okay, so the BRST current was what? JB, I'm writing it all and then we'll take the path that we need, was CB, C times TBM plus gamma times TFM. Okay, plus half, and the other stuff will not matter. CTG plus gamma TFG. Okay, so do you understand every term in this formula? This is the dimension 2 stress tensor for the matter. This is the dimension 3/2 super stress tensor for the matter. This is the dimension 2 stress tensor for the ghosts. And this is the dimension 3/2 super stress tensor for the ghosts. So this was the formula for the BRST current in terms of the T's. Okay. Now we also had that this gamma was bosonized like this. Was e to the power times zeta. Okay. So what we want is the expression for JB on the pole with gamma, because we want BRST charge going around. No, not gamma, this zeta. We want the pole in this expression. Okay. Now, where are we going to get a pole in this expression? The only thing that is non-singular, that has a singular OPE with zeta, is eta. Eta appears only in gamma. So it's the gamma term that's going to give you something singular. Okay? Now, so the gamma term appears here and here. As you will see in a minute, we will only be interested in parts involving the matter. So this part will not be of interest to us. So this gamma, so the part that was of interest to us is going to be e to the power phi times eta times zeta. Z times zeta of 0. This will give us a 1 by z. and there's TFM. So you see that this, for the part involving the matter field, is equal to e to the power phi times TFM. Is this clear?
That is e to the power phi into TFM?
What? This one here? This was e to the power phi into TFM. Right? Because it came from here. We just substituted gamma was e to the power phi times eta and put that in here. Okay? So the part of interest, this is half the solution to the problem I gave you about QB on zeta not involving zeta. This part clearly does not involve zeta. To work out that problem, you have to check that this part also does not here. Okay, that I'm leaving to you. Okay, but we're going to be only interested in the part involving the matter. Now, why are we interested in the part involving the matter? Well, you'll see. Now what we're doing is taking this object, this was x.
That zeta will not be there, right?
This zeta has gone away now. It's just this. This is the answer. So what we wanted was the pole in bringing this whole thing to zeta. The residue of the pole was this. Is this clear? Okay. Now we want to take this guy, which is x, and there's some stuff independent of matter. We'll see in a moment. It doesn't matter. Okay. We want to take it and bring it near one of the e to the power minus phi times O's. So what we've got is e to the power phi times TFM at z. This is also at z. And then we want to bring it near, e to the power minus phi of z times O, times of 0 times O of 0. Now, what do we get? So this part knows only about the matter. This part knows only about the phi. So they decouple from each other. Well, the phi part is simple because it's e to the power phi times e to the power minus phi. Now this OP we know how to calculate, right? Because this OP is e to the power minus 2-point function of phi z, phi 0, and by 2. No, not by 2, right? Because not by 2. Because if I Taylor expanded, I mean, there are many ways of saying it, but I'll just get this replaced by this inner product. This Wick's theorem that we worked out. I was trying to work out the factor. To work out the factor, what I did is I just expanded in my head 1 plus phi. Here I expanded 1 minus phi. That came with the factor of minus, but no 2, and then that's the first term in this exponential. Okay, excellent. So, and then this was equal to what now? Was equal to minus log z minus z prime. In general, we had minus alpha prime by 2, log z minus z prime, log z bar minus z bar prime. But the phi is normalized such that alpha prime was 2. It's one of these fake scalars, right? Okay, and therefore this is e to the power minus log z minus z, in this case z. So the 2 minus signs, so that gives you z. Well, this is familiar, right? We use this while working out that this was the state dual to the n-sector vacuum, for instance. We've done this calculation before. Okay, so what we've got is z times Tf m of z acting on e to the power minus phi. Acting on e to the on O of 0, because we've already dealt with the e to the power phi's. Is this clear? Please stop me if something's not clear. Clear? Okay, but there's a factor of z, and I'm going to take z to 0. Okay, So I will only get a non-zero contribution if this product has a pole. But does this product have a pole? Well, in fact, firstly, TF with O, where O is any primary operator, has no singularity that's worse than a pole. And it does have a pole. Okay, it does have a pole which is given precisely by the action of G minus half on O. Right? Let's remind ourselves of why that pole is related to G minus half on O. It's just because that was the current. Let's remember, there was TF was equal to sum over Gm over Z to the power 3 by 2 plus M. So when M was equal to minus half, this was the pole part. That was the supersymmetric current. Okay, we can do this more formally using contours in the usual way. Okay, so this quantity in the limit Z goes to 0, this quantity in the limit Z goes to 0 is precisely G minus half on O. So it's precisely the integrated vertex operator. And so we now have finally reached something interesting. The interesting thing that we've reached is the following. Instead of working with integrated vertex operators, we can keep all our vertex operators unintegrated. That's what we did in this argument. And instead of saying two vertex operators are integrated, we could say that along with the one insertion of zeta of Z naught, which is always there, we put two insertions of X. Yes, since the answer doesn't depend on where we are, we can then take this X near one of the vertex operators. But we've just shown that doing that turns it into an integrated vertex operator. But this is a much more beautiful way of saying it. Why is it much more beautiful? Firstly, it's clear from this that it doesn't matter which of the operators we choose to be integrated and which not, because it's just a question of where you move the X's, but it doesn't matter where the X's are. But secondly, it suggests something else. And that something else it suggests is the following. It suggests that instead of taking two of these X's to two different operators, we could have, if we had wanted to, taken both X's to the same operator. That will do something, and in particular give you a vertex operator with a net insertion of, you see, each X lowers the e to the power minus phi insertion, removes one factor of e to the power minus phi. So if we took two X's, we would get an insertion with e to the power plus phi. And this is a perfectly legal thing to do. So the operator that you get by taking two picture changing operators near one of the superconformal matter primaries is called the plus one picture version of that operator. The operator that you get when you take three of them is called the plus two picture version of that operator. And now we know, now we finally understand what we have to do in order to define scattering amplitudes and arbitrary genus surface.
So you put positive number of X's.
Yes, exactly. We will firstly put however many vertex operators we have. That gives the next net phi charge. Let's say we have R vertex operators. That gives the next net phi translation charge as minus R. But we want the net phi translation charge to be G minus 1 times 2. Right? We want that, because otherwise the integral will be 0. So that tells us that we have to insert G minus 1 times 2 plus R picture changing operators. Right, g minus 1 times 2 plus r picture changing operators into our game. If g is 0, that is r minus 2, which tells us that 2 of the vertex operators have to be left in the minus 1 picture, the rest have to be in the 0 picture. That was our old result. Okay? But if g is 0, then we would put as many picture changing operators as there were vertex operators. So one option would be to take one picture changing operator towards each of the vertex operators and make them all integrated. All 0 picture operators. That was also our old result for the torus. Sphere and torus we had previously. But now suppose we are in genus 2. Now if we have R operator insertions, we will put R plus 2 picture changing operators. And now you see it will be impossible for us to work only in picture 0. Because these picture changing operators, say you take one for each of the R operators, there are 2 left over. So you'll have to take these 2 somewhere. And if you want to associate them with the vertex operators, you take them to the vertex operators. 2 of the operators will become the plus 1 picture operator. Okay? So this is the best way of saying it. Put g minus 1 times 2 times g minus 1 plus r picture changing operators into your path integral. Remember that all of this always also has that additional insertion of zeta of 0 itself. Plus we've got the insertions associated with our scattering states. Okay? And now you go ahead and compute your scattering amplitude. Okay, there's one little subtlety that's left over, having to do with the 0 mode of that other eta field, but we'll come back to that in a little bit. First, I want to make sure you understand everything we said today. Do you have any questions?
Insertion of x's doesn't have any extra cost, or you can just...
Insertion of x's is needed.
Yeah, I mean, so does that also bring in some new term, or... I mean, it's not identity.
It's not identity, no. If it was identity, it would be bad, because without the x's, you're going to get 0. Right? The phi integral kills you. So it's needed. It's putting these these x's is not changing the answer from something you previously knew to be the right answer. Putting the x's is the answer.
Yeah. And if you do through path integral,
It will come with these x's. Okay? So, up to this one last little subtlety, which I'm tempted to defer for a while, up to this one last little subtlety, we are through now. We have completed our statement of the rules for computing string scattering amplitudes. Okay. Now let me just check if there's something in Pulchinski's book that about in this part that I have not talked about. And otherwise we will either break for today or start. Yeah, I think enough formalism for now. This is, where you start encountering the subtleties is at 2 loops. For now, forget it. Let's start computing. All the principles are in place. But let me just check if Pulchinski says something that is important that I've missed. He talks basically the rest of the formal stuff that we've not discussed is his discussion of how you can see the same stuff from integral over supermoduli space. I'll forget that for now. Okay, it's too much formalism. Okay. Maybe at some point we'll come back to that, think of it that way. But for now, okay, good. So we now have the rules in place for computing all string scattering amplitudes. These rules may seem a little complicated and a little abstract. In reality, they're neither particularly complicated nor particularly abstract, at least for simple sphere and tree and torus diagrams. But by far the best way of saying that is now to start doing actual calculations. Okay? So now in the rest of this course, what we will do is to take this formalism we have developed and try to use it to actually understand some physics in string theory. Okay? So we will try to use it to actually try to develop. We will the first thing I plan to do is to calculate a bunch of tree level string scattering amplitudes. Okay. One of the things we will see in this is the Virasoro-Shapiro amplitude. Okay, the famous Virasoro-Shapiro amplitude. Okay, then we will discuss string theory at one loop level. And we will learn a lot of physics from discussing string theory at one loop level. Okay. Then we will go on to a discussion of toroidal compactifications of string theory, a more serious discussion than we've already had. We'll discuss D-branes, and then maybe we can come back and start looking at string dualities and maybe ADS, AFD, that kind of thing. Okay, so that's the plan for the rest of the course. The formalism, which is understanding the string world sheet and understanding the rules for string perturbation theory, which involved a lot of the heavy lifting, is now basically done. Okay, now we get to use some of this. So maybe in the next 10 minutes, we can start just as a warm-up, doing some string scattering amplitude calculations. Actually, maybe it's better to start that next time, because then maybe it's better to stop this here and start this next time. Okay, so the next class, which is on Friday, we will start calculating various string scattering amplitudes so as to start getting a sense for what's going on in